You ever flip a switch and the lights just come on? Of course you do. But behind that simple little act is a massive, continent spanning machine that's, believe it or not, constantly on the verge of collapse. Today, we're going to dive into the incredible engineering that keeps it all from falling apart: power system analysis. So, let's get right into it. At any given moment, our power grid is getting hit with all sorts of disturbances. So, what in the world is the invisible force holding this whole thing together? Well, the answer lies in this continuous, super high stakes balancing act that engineers are performing every single second of every single day. To really wrap our heads around this, let's use an analogy we'll keep coming back to. I want you to imagine that every major power generator is a huge truck driving up a steep hill. Now, they're all tied together by these incredibly strong rubber bands, and here's the kicker: they all have to travel at the exact same speed. If even one truck suddenly speeds up or slams on the brakes, it puts a ton of stress on all those rubber bands. If they snap, the whole convoy goes crashing down. That, right there, is the challenge of grid stability. So here's how we're going to break it all down. First, we'll talk about the fundamental rule of the grid. Then, we'll see how engineers actually map the whole thing out. After that, we'll look at what happens when things go wrong, and the crucial analysis that figures out if the system's going to survive. We'll then get into what we call the 3 flavors of stability, and finish up by looking at the challenges ahead. Okay, first things first, let's talk about the core principle here. The power grid isn't like a water reservoir, You can't just fill it up with electricity and draw from it later. No, it operates in real time, and it demands this perfect, instantaneous balance. And I mean that literally. Every time you turn on your TV, or a factory fires up a machine, or you plug in your phone, a generator somewhere on the grid has to spin up and produce that exact amount of power in that exact instant. If generation and consumption are even slightly out of whack, the system's frequency, its very heartbeat, starts to drift. And that is the very first step toward a major blackout. So because this balance is so delicate, you can imagine engineers need a map, right? They have to know what the system looks like under normal, everyday conditions. And that's where their first big tool comes in. It's called a load flow or power flow analysis. A power flow study is basically the grid's GPS. It solves this massive set of incredibly complex equations to tell engineers the voltage at every single connection point, which they call a bus, and exactly how much power is flowing down every single transmission line. It's like taking a perfect high-resolution snapshot of the entire system's health at one moment in time. And you really can't overstate how important this is. I mean, think about it. You can't possibly predict how the grid will react to a crisis if you don't know where it's starting from. This snapshot, this pre-disturbance picture, is the absolute foundation for everything else, for fault studies, stability analysis, and even for planning where to build new power plants decades from now. And this kind of breaks down how it all works. First, engineers create a digital twin of every single wire and transformer. Then, they plug in all the data on where people are using power and what the generators are doing. They built this huge mathematical model of the whole thing, and then they unleash some serious computing power to solve it. The result is that crucial snapshot: all the voltages, where all the power is going, and even how much energy is being lost to heat along the way. Okay, so that's the grid when everything is running smoothly. But it doesn't always run smoothly. Things go wrong. A lot. So what happens when the system gets hit by what engineers call a fault? At its heart, a fault is just a short circuit. It's some kind of abnormal connection that creates a path of least resistance, causing a massive, and I mean massive, surge of current to flow where it shouldn't. This is the disturbance. This is what rocks our convoy of trucks and seriously tests the strength of those rubber bands. And these aren't some abstract, theoretical events. The causes are things we see all the time: a lightning strike zapping a transmission line, a tree branch falling during a storm. Heck, even a squirrel getting into the wrong place at the wrong time can trigger a major fault. These are the real-world events that can lead to blackouts. Now, faults generally come in 2 main flavors. On the one hand, you have unsymmetrical faults, like a single power line touching a tree branch. These are by far the most common thing to happen. But on the other hand, you have the rare ones, symmetrical faults, where all 3 power lines short-circuit at once. And engineers spend a ton of time studying these because, even though they're rare, they typically create the most violent currents and put the absolute most stress on the entire system. So, a fault happens. A lightning strike hits a major transmission line. A massive surge of current rips through the system. The crucial question for engineers, and really for all of us, is what happens next? Is the system going to recover, or is it going to collapse? This is the whole ballgame. This is power system stability analysis. All right, so this is the official formal definition from the big engineering groups. But the keywords to focus on here are regain a state of operating equilibrium. See, stability isn't about preventing bad things from happening. That's just impossible. It's all about designing a system that is tough enough to take a punch, survive it, and settle back into a new, stable normal. Now, you might think stability is just a simple yes or no question. Is it stable or isn't it? But it's way more complex than that. So engineers break the problem down into different categories based on the physics involved and how fast things happen. And understanding these is really the key to understanding the grid. And just take a look at this chart. You don't need to read all the tiny print, but just see how they take this one big problem of power system stability and split it into these three main branches: rotor angle, frequency, and voltage. Each one of these describes a completely different way this system can fail, a different kind of crash for our convoy of trucks. So first up is rotor angle stability. This one goes straight back to our analogy. It's all about whether the generators, our trucks, can stay locked in sync with each other after a big disturbance. A fault can cause some generators to speed up and others to slow down, and that stretches those metaphorical rubber bands. If they stretch too far and snap, the generators fall out of sync, and that can trigger a cascade of failures across the grid. Next, we've got voltage stability. Think of this as the electrical pressure in the system. A major disturbance can suck up a ton of a specific kind of power, called reactive power, causing the voltage to plummet. The ultimate failure here is something called a voltage collapse, which has been described perfectly as that weird phenomenon where you turn on one more light bulb and the whole room actually gets dimmer right before all the lights go out for good. And finally, there's frequency stability. This happens when a huge power plant or a whole city suddenly gets disconnected from the grid. All at once, you have a massive imbalance between generation and load. This is like our entire convoy of trucks suddenly losing a major engine. The speed or frequency of the whole system will start to drop. The big question is, can the other generators ramp up their power fast enough to stop the fall and restore the balance before the frequency gets dangerously low? So for decades, engineers have gotten really good at these kinds of analyses, all for a grid powered by big, spinning, conventional generators. But the grid is changing, and it's changing fast, and that's bringing a whole new set of challenges to the table. The big deal here is a concept called inertia. See, traditional power plants have these huge, heavy turbines that are always spinning. All that physical rotating mass acts like a giant shock absorber for the grid. Think back to our trucks. They were heavy, right? Hard to push off course. But solar panels and wind turbines, they connect to the grid with electronics. They have no physical spinning mass, no inertia. So as we add more and more of them, our convoy of trucks effectively gets lighter and lighter, meaning a single bump in the road can send them careening off course much more easily. And that really leaves us with this final question to think about. This whole invisible, incredibly complex world of analysis that has kept our lights on for a century was built for a very different kind of machine. So as we build the grid of the future, the fundamental challenge is still the same. We have to maintain that perfect, delicate balance. But the tools, the techniques, and the very way of thinking that we need to achieve it, well, they're going to have to evolve just as quickly.